Hello, everyone. Welcome to Chemistry with Professor John Nguyen at Victor Valley College. All right, now, when you're on the Canvas, this is Organic Chemistry 1, Chem 281. When you're on the Canvas website, the week 1 to week 5 module will have your study guide in there, okay? The study guide shows chapter 1 to chapter 5. We only need 1 to 4 for our first exam, okay, which come in the week number 4. All right. If you're in the 2-day class, will be the second day of the week. Okay, for chapter 1 to chapter 4, the first 2 chapters are mainly review that we did a little bit of practice in the class. The first thing, these are informations you can read on your own. Why organic chemistry. It gives us good knowledge, to explain a lot of things out there, like transformation, functional group transformation of acetaminophen, which is Tylenol. They get converted to, different functional group. Like notice the OH on acetaminophen become the ketone there. So anyway, and the toxicity and all that stuff. Now, if you remember General Chemistry 1, we talk about electron configurations. It's good to go back and review this stuff. A type of bond, like ionic and covalent bond, but for us, we'll focus on covalent bond, okay? Covalent bond. Now, the covalent bond consists of electron that share between the two atoms, all right? And that's when you make that connection, you make that bond between them. And you can have a single bond, double bond, and a triple bond. And that's the process, and that's one of the steps when you do the Lewis structure, when you draw the structure of a molecule. Okay, so Lewis structure, here's an example, a very good one. You have condensed structure, Lewis structure when you show all the dots and about to connect them. And then the line angle formula, that's the best one because it quicker. You don't have to write the carbon out, you don't have to write the hydrogens. You only have to write out what not, if it's not carbon or hydrogens, okay? So that's really nice about line angle formulas. Saves you a lot of time, okay? The one thing to remember is octet rules. So if you notice, carbon has 4 bonds. So, and then 4 bond for a single bond, that's 8 electrons. Octet means 8. It can be a combination of 1 bond and 3 lone pair. For example, on this structure right here, you guys see the bromine right there has 1 bond and 3 lone pair. That make it 8. That's also octet. Look at oxygens. You see oxygen double bond with carbon. That's 2 bond plus 2 lone pair that make oxygen octet. Okay, so that's 4. Any combination is good. Polarity of the bond, that depends on electronegativity. So for example, CH bond, if you take the carbon, which is 2.5, minus hydrogen, which is 2.1, the difference is 0.4. So if the difference is, you always take the larger electronegativity, subtract the smaller one. Now if the difference is 0.4 or less, that will be a non-polar bond. If the difference is 0.5 or more, that will be a polar covalent bond, okay? Now if a molecule, listen to this carefully, if a molecule has only non-polar bonds, overall molecules should be non-polar. That's common sense, right? However, if the molecule has some polar bonds, and they cancel out perfectly, the molecule is also nonpolar overall. Okay, if the polar bonds don't cancel out in the molecules, the molecule become polar overall. Okay, formal charge, that's the charge that result in um, an atoms when there's a difference between overall atoms electron, and there's an addition of electron, or there's a loss of electron. Okay, so if oxygen has 6 valence electron but end up in the molecules with 7, then it's going to be -1. Okay, like for example, oxygen with 3 bond uh, and 3 lone pairs and a single bond. Resonances, we did some of those in the class when we move the bonds around and move the charge around. That's the resonances, keeping everything else the same. We don't break the atom and connect somewhere else. Okay, that would be resonance. Okay, we got a couple examples for you guys to practice. And here is what I'm talking about. Okay, now this is the bonding pattern. If you notice, carbon neutral, the middle column neutral, carbon has 4 bonds. Notice the wedges bond mean headed towards you, and the dash bond mean heading away from you. The solid one line, those are the ones right on the surface. Okay, notice carbon, if it has 3 bonds, that's missing a bond, and that will bear a positive charge. If carbon has 3 bonds and a lone pair on the right column, you guys see on the right column, that would be a negative, okay, because it's got an extra electron. All right, same pattern, for other things, and that's a typo right there. That's nitrogen's. Boron has its own. Boron is the first row, and then carbon, and then nitrogen. So that should be nitrogen instead of boron for nitrogens. And oxygen too, okay? Chlorine, those are the bonding pattern. If it's not neutral, if it's something else different, it's going to be either negative or positive. Anything is possible there. Okay, now we're moving on to structure, okay? When you bring atom together and connect them together, we're creating a bond. Now, sigma bond is the first connection between 2 atoms. If you connect carbon and hydrogen, that bond is a sigma bond. Now that's it. Carbon and hydrogen cannot form another bond. But however, when you do carbon oxygen or carbon carbon or carbon nitrogen, there's a possibility that you can connect more, up to 3, okay, bond. So when you connect 2 carbon together, the first bond is called a sigma bond. That's the in terms of orbital overlap, it's going to be direct head-to-head overlap. If you want to build a second bond between the 2 carbons, you have to do the pi bonds, and that's pi bond is the result of 2p orbitals overlap in a parallel fashions. Okay, so every time you have a bond like a sigma bond, you do have a sigma asterisk or a star. That's called an anti-bonding. Okay, that's the one with higher energy. All right, now same for pi bond. Okay. Okay, hybridizations. Now we do have, if you remember in general chemistry, we have different hybridizations like sp, sp2, sp3, and that apply for carbon and other atom as well. So review those stuff, and it's right here. Hybridization from carbons and how they arrange in space. sp is going to be linear, one on the left, one on the right. sp2 is like a triangle spreading out at 120 degrees, and then sp3, that would be a tetrahedral with a bond angle of 109.5. And here's some of the example. Beryllium bonded, on one on the left, one on the right, and that's sp, very simple sp, linear. bond angle 180. Boron, which is BH3, you got 3 hydrogens, so they spread out evenly, and that make it a perfect equilateral triangle. That's sp2, right? sp3 carbon is a perfect example, like CH4. When you have sp3 and you have 4 of them, and they are connected, 4 orbital connect to 4 hydrogens in a like a pyramid, known as tetrahedral shape. 109 should be 109.5 as well. Now talking about multiple bond, okay, between the 2 carbon, we want to connect the second bond. That will be that will be pi bond. In order to do pi bond, we have to have sp2, so that way we have a pz available. You notice pz on each carbon. Okay, so on 2 carbon, the 2 pz interact with each other parallel. That create the pi bonds. All right. And you can see the molecular orbital presentation right there, all the orbital overlap. Now triple bond would be sp, because you want py and pz available. And you got 2 set of p orbital. So every time you have a triple bond, the first one is a sigma, and the last 2 bonds are pi bonds, pi 1 and pi 2. We cannot have 2 sigma bonds between the 2 atoms. Okay. Now, when in terms of bond rotations, if you have a single bond between the 2 atoms, they are free to rotate left, right, top, bottom, rotate, okay, easily. However, if that's a double bond, that's a restrict rotations, meaning it's going to cost energy. Okay, so other than that, it's got to stay. Just like you hold, if you play racket, some sort of racquetball, you hold a racket by one hand, you got more freedom to rotate that racket left, right, or top, bottom. However, if you hold something, a racket, like tennis racket or some, you hold with 2 hands, it's gonna be harder for you to rotate. Okay, and that's what we call restrict rotation. It costs more energy to rotate. Okay. It's a couple additional problems for us to practice. Okay, and now we're looking at the structure more. Isomers, we got different kinds of isomers. Constitutional isomers, known as structural isomers, or stereoisomers. Bond polarity, intermolecular forces, like the force that hold molecule together. And focus on the 3 main one, the dipole-dipole force. The first one, dipole-dipole, that exists in polar compounds or molecules. London force, also known as dispersions, that exists in non-polar molecules. And then finally, hydrogen bonding, very special polar, for specially polar molecules with oxygen, nitrogen, or fluorine. Okay, those are the essential atoms in those molecules that create an interaction with the hydrogen, known as hydrogen bonding. Very polar compound. Okay, so if you have alcohol, you have amine, they're very soluble in water because they do hydrogen bonding with water. Solubility, if you have 2 compounds with similar or the same polarity, they will dissolve in each other, okay, if it's liquid. But if you take like gasoline and non-polar and water, it's polar, they don't dissolve in each other. Functional group, there is a separate table of functional group, but the popular one that we need to know for the test would be the alkene, alkyne, aromatic hydrocarbons. Be able to recognize them, identify functional group. Okay, if you see a double bond, it's an alkene. You see triple bond, it's an alkyne. You see a cyclohexane with 3 double bond, that's aromatic. Okay, alcohol, you gotta have OH, any compound with OH. Oxygen in the middle of the molecules, carbon on both sides, that make an ether. Aldehyde ketone, that's aldehyde is C double bond O, and that's a hydrogen on the carbon. Ketone, C double bond O, on the left of that carbon, on the right, no hydrogens. Connect to another carbons. that will be ketone. Carboxylic acid, you have to have a C double bond O and the OH right next to each other. That's carboxylic acid. So we call it COOH, right? Carboxylic acid derivative like ester, um, acid chloride, so on and so forth. So this is a good example here. Identify functional group of molecules on this page. Going from left to right, the first row is an aldehyde because it's got C double bond O and hydrogens. The second one is acetone, a CH3 on both sides, double bond O in the middle, that's a ketone. The third one is acid chloride because it's got the double bond O, that's a ketone, and chloride, we call it acid chloride. Look like the cyclohexane with the OH, that is alcohol. And the cyclohexane with a C double bond O, that's a ketone. Okay? So on and so forth. Nitrogens, if you got nitrogens, compound with nitrogen, that would be called an amine. If you have a compound with nitrogens, and right next to the nitrogen C double bond O, that will be an amine. And finally, the one on the right here, the one on the right, is C triple bond N, that's nitrile functional group. Nitrile functional group. C triple bond N, okay, that's nitrile again. Additional problem for practice. All right, finally the acid base. For this review, acid base, if you remember general chemistry 2, looking at pKa, given pKa, notice on the left side, the strongest acid on the top, that's the one with the lowest pKa, like negative. If you look at the column on the right, it's the base, weakest base on the top. So the stronger the acid, the weaker the base. You go all the way to the bottom, weakest acid has a pKa of 50. That's CH3. If you manage to pull off the hydrogen from that, doesn't matter on which side, CH3 becomes CH2 minus. If you manage to pull that hydrogen off, it becomes extremely strong base. Okay, we need something extremely strong to pull that off, pull up that hydrogen from the carbon. So that's so the weaker the acid, the larger the pKa, the weaker the acid, the stronger the conjugate base. Cool. All right. So that's the review. I mean, just basic stuff. If you know how to draw resonances for the same molecules, if you know how to draw different structure, that's structural isomers for the same formula. Okay, that would be called structural isomers, and be able to identify what type of isomers, and you should be good. Be able to identify which acid is stronger, okay, based on pKa. All right, so that's the first chapter 1, chapter 2 review. And the next video we're going to go into the very first organic compound, that's alkanes. All right, thank you for watching, everyone.